Hi everyone. The 2-3 homework quiz was originally scheduled for today, which is the next class. We're going to use today as a swim our heads up above water day, because we probably felt like we got buried a little bit in the last lecture. So today the plan is you guys fire away questions, homework or clarification or whatever at me. We'll try to clean up where you guys are at, so you leave feeling better, ideally a lot better than you did when you walked in the room, 3 minutes ago or whatever. Cool? And that's the plan for today. Like, no forward motion. This is pause to let you guys swim up to the surface so you feel less underwater than you did at the start of class today. Deal? Yeah, for sure. Who would like to start?
I just wonder, can we ask you questions from our Delta math too?
Sure.
Okay. Just like the limits to infinity ones.
Okay. So let me pull up the delta math here. And we'll take a look at that type of question. I obviously won't do the same one that maybe you saw, but like, whatever, it's good enough, right? And you're looking at the analytical limits. And we're looking at limits to infinity. Any of the types is probably fine.
Just any, yep, I'm sure I understand.
So, when I'm looking at a limit where x goes to infinity, the first thing I'm going to do is I'm going to approach it the same way I would if x was going to a finite value. I'm going to think about doing like a little quick direct substitution. Now it's going to be kind of dirty because you don't actually get to plug infinities in. But like, I have a polynomial that's positive, going to infinity. The y goes to infinity, right? I have another polynomial whose leading term is positive. Again, the y goes to infinity. This is like infinity over an infinity. It's like an indeterminate. Okay with that? Now the difference is going to be if I have a limit where x goes to infinity and it's indeterminate, I'm not going to try to factor and reduce. I'm not going to multiply by conjugates. I'm not going to FOIL things out. I'm not going to do any of that nonsense. I'm just going to use my growth rates. Okay? So if I look at the numerator, what's the fastest growing piece of the numerator? The x squared part, right? If I look at the denominator, what's the fastest growing part of the denominator? The x to the fifth part, right? Which one is growing faster, x to the second or x to the fifth? X to the fifth, right? Everybody good with that? So if the bottom is growing faster than the top, the bottom's going to get very, very big compared to the top staying relatively small. If you have a little number over a big number, that's going to zero. So that would be all I would do here. So I'm not writing anything down. There's no work to show. All I'm doing is just thinking about this in my head. And
oh, so it's like bottom and bottom.
Same.
What's that?
Bigger on bottom 0, right?
Correct.
Okay.
Yeah.
And then bottom needs bigger on top.
Top is not.
That'll be either positive or negative infinity for us, because of what it means is there's from the rational functions, it meant there's like a slant asymptote or some other polynomial asymptote where it's going to be going to either positive infinity or negative infinity depending on the specifics. So there you have to do a little bit of investigation, but you know it's going to be one or the other. And then if they're equal, it's leading coefficient over leading coefficient. Right? So if we look at this one, notice the numerator is two things multiplied together. So that's really just like one thing, right? The multiplication going together. What's the degree of the polynomial in the numerator?
X squared.
Degree 2, right? X squared. Everybody agreed?
Yeah.
Because it's a linear times a linear, so you should have a quadratic.
Oh.
In the denominator, what's the degree of the polynomial?
Square.
4, right? A cubic times a linear should give you a degree 4. Which one's growing faster, 2 or 4? 4. Where's this going?
0.
0. Is everybody okay? Again, I'm not doing any kind of calculation here. I'm just kind of looking at it and using what I know about the growth rates and my rule from yeah, that's it. From that Mr. Myers taught me last year, which you guys all seem like you know really well, and I don't want to get in the way of that, but I have no clue what the acronym is standing for. But if you got it, you got it, and I'm happy that you have it.
I know exponents are the same divide coefficient. That's what you just see.
Okay. Thank you.
Divide coefficients isn't equal.
It's equal in
Each DC.
something. Exponents are the same.
Bigger on bottom 0.
Divide coefficients.
Yeah, right.
Lucia, should we go to type 2?
Yeah, I would just how would you do it if they're the same top and bottom? Like I have one pulled up and they're the same coefficient numbers on the top and on the bottom.
Let's look at this one.
Okay.
What's the degree in the numerator?
4.
4. What's the degree in the denominator?
4.
4. So this is going to be divide the coefficients, right?
Right.
So what will the leading coefficient be in the numerator?
16.
Negative 16, right? Negative 4x squared times positive 4x squared should be negative 16.
Mm-hmm.
What's the leading coefficient in the denominator?
Negative 6. Negative 6x cubed.
3
Negative
Oh my
3x
God,
to the 4th, right? You care about the x terms multiplying together, right? That'll give you the leading coefficients. So that would be negative 16 over negative 3, or really just 16 over 3. Yes.
If the exponent is bigger on top, then it's like there's no slant asymptote.
Correct. So the limit will either go to positive infinity or negative infinity, because what the bigger on top means is that there's going to be some kind of polynomial shaped asymptote. Whether if it's a linear, it'll be a straight line. It could be like quadratic.
Mm-hmm.
Could be like cubic or something. Like it could be really weird. But the idea is that the end behavior is going to be shooting off either positive or negative. It's going to be one or the other.
So is it that there's no asymptote or there's no slant asymptote?
So there's no horizontal asymptote,
Horizontal.
but there will be some kind of polynomial shaped asymptote.
Okay.
Whether it's linear, quadratic, or cubic, or whatever.
I get it.
But for the limit part, it just is telling us that it's going to have a polynomial end behavior, either positive or negative infinity.
So then I want to show you this question, how it worked, but I don't want to take over the class's time. Something like this. Because that would be cubed on top, it'd be squared on bottom. That'd
Right.
be bigger on top.
So Brooks is looking at one where it's a cubic on top and a squared on bottom, and wants to try to figure out whether it should be positive or negative infinity. To do something like that, what I would want to do is I want to look at the coefficients on those on the two leading terms. In the numerator, the coefficient, is it positive or negative?
Well, it's like in factor form, so it's like it is all positive, but
So you look at the 2x term, so you have 7x times 5x squared, so that's positive leading coefficient. In the denominator, the leading coefficient would be negative because it's 5x times negative 5x. If you have positive over negative, that should be going to negative infinity.
Okay. So then the limit's negative infinity.
Yeah, it might. I would probably want you to write does not exist though.
Okay.
Unfortunately, so it's a matter of preference early on to whether we define a limit existing when it goes to infinity or negative infinity. In the beginning, many places will say that just those limits do not exist because they're not finite. Eventually, they're going to ask, we're going to define an infinite limit and start talking about those. I would just assume do it straight away because it's not that big of a stretch. Like, why get used to writing does not exist and be like, oh, no, now we're not going to do that anymore. We're going to say positive negative infinity. Here, I think that's probably what they want you to do, Brooks.
So either if it's bigger on top, you look at the coefficients, or if it's the same, you also look at the coefficients.
Yes, the coefficients will give you a finite number. Bigger on top, the coefficients will just tell you positive or negative.
Okay, cool. And then that'll tell you either positive infinity or negative infinity.
Correct. But in the delta math, it just doesn't exist either
Okay.
in the end. Yes,
Is it just
Frankie, right?
Yeah.
Okay, I'm just still working on names, and I haven't talked to you a lot, so that's it for me.
Is it just the numerator that determines whether it's positive or negative?
No, it's going to be the coefficients. So if I had a positive coefficient on top and a negative coefficient on bottom, that's going to make like a negative polynomial.
Mm-hmm.
So it doesn't matter if it's an even degree or odd degree, a negative coefficient is going to send it to negative infinity. Whether it's odd or whether it's even, it'll still hold.
Okay.
Does that make sense?
Yep. Thank you.
Brooks.
Just for the delta math, is it everything in analytical limits?
That delta math hasn't been assigned yet. That would be what I made this for you guys to practice for for the quiz coming up. Like I think this is probably, the analytical limit stuff is probably pretty good practice for that 2-3 quiz.
So then, I'm sorry, how do you find, like, what's all you do on, like...
So if you look at the past due tab,
Yeah,
it had the old delta math on there that we did part of, but maybe you didn't finish.
I only saw August 24th.
Yeah, so that, when I make a delta math assignment, to make one requires me to put in a due date.
Okay.
So I just freaking guess at something, I write it in. The delta math due dates don't mean anything. You can, use them to wipe your behind with. My Notre Dame in the assignment will have the actual due date that I'm looking for. Even if the delta math says this is past due, so you get 0% on it, I can see the completion percentage on it, and that's what I'll use when I'm checking. I don't care about like your percentage on delta math. I care about the percent complete. So I can see that regardless of when you do it.
Alright.
So will the analytical limits be next Sunday?
Sure, that would be fine. Yes. But again, like, they're here for practice, right? So I made this because it seemed like after the end of last class I knew that we weren't there yet. So I let it simmer, like, here's some more practice. I was ready for it for first hour because I kind of had a feeling what was happening. But, Mark.
On a test or something, when you see a limit that approaches negative,
Sure.
do you make any difference?
The only place where it could possibly make a difference is when you have bigger on top. That's the only place it would make a difference. Doesn't make any difference with respect to bigger on bottom than on top, or when they're the same. Only on top, because they are the odd degree, the degree of the polynomials matter to whether it's going to positive infinity or negative infinity. Does that make sense? So it's just like, it matters in one of the scenarios, and only just a little bit in terms of figuring out the sign of positive infinity or negative infinity. Lucia? And then we'll get you next.
Yeah, then fine.
So in the book, it tells us for one of the questions, it asks us to evaluate the limit. Does that mean the same thing, or is this like completely different? Same thing.
Yeah. Evaluate limit means tell me what it's equal to.
Got it. Okay.
Brooks.
So it says chapter 2 delta math number 1, but in mine it just says like limits from graphs and tables.
Yeah. That's the first delta math I assigned for chapter 2.
Okay.
So that's the assignment that's due on Sunday.
Okay, and did you have to do it all or just those 4 sections that you told me?
You should finish it out.
Okay.
So I think I assigned part of it, and then like we came and talked the next class, and it's like, okay, you should now be able to finish this because we did a little bit more and way more than that. Kept on going, and I got excited and talked about probably more than I needed to, and sometimes that happens.
That's okay.
And it's okay, because I'm aware that I do this. Like I jump ahead, and it's like, oh, that was we just did a whole bunch of stuff, And I look back, I'm like, I did not need to do as much as I did. But it's just like this build, this, you know, like that's where all this stuff is connected to me. So I want to just keep like building the connections out. But then I acknowledge that there's going to be times where we now need to pause and like go back through and like reflect on the details and help you guys get like process the big chunk of stuff that you just got thrown at, you know, that just got thrown at you. Should we do some more examples? Do you want to continue doing some of these other types, Adriana?
Can we try a piecewise one?
Sure. That was up farther, right?
Yeah, I think this is first.
Yeah. Sure. So it says, for the function below, determine limit as x approaches 1 of f of x. So, for the limit, a general limit to exist, the left-hand limit has to equal the right-hand. So what I'm going to do is I'm going to look at the limit as x approaches 1 from the left, which would be using that piece, and the limit as x approaches 1 from the right, which would be using that piece. Since both pieces are polynomials, I can evaluate the left-hand limit and right-hand limit just by using direct substitution. So I'm just going to plug 1 in here. When I plug 1 in, I get
-1.
3, right? If I plug 1 in here, I get 3. So the left-hand limit equals the right-hand limit, which tells me the general limit is 3. Is that?
Yeah.
Okay.
Yeah.
So, so the order of operations says you square first and then make it negative.
Okay.
So exponents comes before multiplication. Technically, the negative sign is like -1 times
Okay.
stuff.
Yeah. Yeah.
Brooks?
I have one on Delta Map, if I could show you. It's from the chapter 2 homework I was just talking about.
Okay. One moment.
Yeah.
I want to make sure, Adrian, do you want to do another of these before I move to something else?
Can we try one that like doesn't do it?
Well, I mean, it's just like whatever it gives me. But I'm going to, so this one, it says the limit as x approaches -2 from the left. So which piece is coming from the left? The less than, right? So I'm just going to do this. So all I'm going to do is plug -2 in, and that should be my limit. Because again, it's a polynomial, I can just direct substitute it.
Yeah.
Okay?
Thank you.
So 2 minus 4 is just 2.
-2.
Yes, -2. Yes, that's what I that of course, -2. That's what you guys are there for, to catch it when I say something wrong. So that's excellent. Adriana, feel okay?
Yeah, thank you.
So again, like, if it's a general limit, I check both. If it's a left-hand or right-hand limit, I just need one piece or the other. And they're probably all going to be ones that will be direct substitutable. So again, piecewise, usually pretty easy to deal with. It's scary to look at, but it turns out to be like, all I'm doing is just direct substituting. Like, I just have to use the right pieces. Brooks, I think, is next, then we'll come back. Yes, sir.
It's from the other one where it's finding limits from the table.
Okay.
Yeah, that same one. Is that? Oh, mine is -4 from the left-hand side, but yeah.
So the pieces I would pick then, if I'm doing -4 from the left, I do like -4.1, -4.01, -4.001, -4.0001. Here, if I'm going to -infinity, I would do like -10, and then like -100, and then like negative, oops, not P. It's not gonna know what to do with that. Negative 1,000.
Can you do that?
And then like negative 10. I just use power. I always do powers of 10, like orders of magnitude. Just feels like it makes most sense to me. If I look at this though, is this settling down to a specific value? No, it's kind of bouncing around like, right? It got smaller, then it got bigger, then it got smaller. What do you think's going on here?
Does not.
That's what I think too. So you're just kind of looking for a pattern there. If you see it, it'll be obvious. If it's like, I don't see what's going on here, it's probably because it's just oscillating back and forth, not settling down to anything. Right? Like if I look at the limit as like sine goes to infinity, does that limit exist? No, because it just keeps doing this. It doesn't settle down to a specific value. So so we've seen two ways now that limits can fail to exist, right? One is where their left-hand limit doesn't meet their right-hand limit. The other is just like, it's just oscillating back, it's bouncing around too much for it to make any kind of statement about where it's going to end up. Does that feel okay?
If you were to have one of those questions on the test, would this be like re-plugging the y1 thing to our calculator?
Yeah, absolutely. You could absolutely do the same
Yeah.
tabular thing with your calculator just by plugging the function into a y1. Or I could give you the table already
Okay.
and ask you like, what does this table tell me?
Okay.
And you'd be like, oh, this table tells me the limit as x approaches negative infinity doesn't exist.
Yeah.
So it could be I.
Okay.
Whether you have to make the table yourself or you just have to look at a table here.
Yeah. Okay.
So I have this different one where it's the limit as x is the general limit as x reaches. That's general limit, right?
Yep.
Yeah, as x reaches 3, and then I put 2.9, got that number. 3.1, got that number. Then I just did 3, then I got negative 10.
Well, the 3 is immaterial
Okay.
because you have to look at the left hand and right hand limit. So I would do like 2.99 and 2.999 and 2.999, and I would do 301, 3001, 3001, and see if those values are heading towards something, because it looks like they're kind of heading towards 0.6 maybe.
Yeah. Okay,
So that or negative 0.6, I guess, that might be what I'm thinking this is. So you're seeing something where it's like coming to an open circle, and then there's a point above it.
So then why is it when I put in 3, it just did negative 10?
Because what you're seeing, what to me this is telling me is the graph is going to like a discontinuity, and then it's like a remove discontinuity here, and the point is to find somewhere else, which is there's a discontinuity.
I get that. Okay, thank you.
That's what it says to me, but I read that. Lucia, you have those.
I do.
Okay.
So for the limits to infinity again, can you go through one that has like a square root on the top of the fraction?
Absolutely. So just go back to this guy, and I think that was
it's
the
type
type
2,
2
yeah.
ones.
Yeah. Oh, that's a cube root, but yeah, same.
Close enough, right?
Does it matter?
Doesn't.
Okay.
The approach on it takes exactly the same.
Okay.
So if I look at the numerator,
Mm-hmm.
there's a cube root, but that's fine. I'll deal with that in a second. If I look under the cube root, what's the biggest or the fastest growing thing in there? X to the 10. So if I do the cube root of x to the 10, that's like 3 1/3 is the degree,
Yeah.
right? Because the radical's the same thing as dividing
Mm-hmm.
the exponent.
Okay.
Good?
Yeah.
Okay. That makes it.
Oh no, I was just
Okay.
confused.
The denominator, the fastest growing term is
X to the third. Or X to the fourth. Sorry.
x to the 4th. So the degree in the denominator, 4,
Yep.
bigger than the degree of the numerator, 3 1/3. So what does this
Okay.
go to?
Bigger on 0. Oh. Okay. And so if it's a square root and it's the
If
biggest
it's
one is
any
X
radical.
to the 6th.
Any radical,
Uh-huh.
I'm just going to take the biggest degree term and divide it by the index. And
Got it.
that's like the degree for the numerator.
Okay.
Or the denominator, wherever the radical is.
This bigger on top is not existent. Ooh. Okay.
Does that feel good?
Mm-hmm.
Okay. Sam,
I already covered this one.
no, go ahead.
Still a little confused. Run this one on the 2.2 homework.
The 2.2 homework
Yeah,
from the book.
from the book, yeah.
Yeah, happy to do it. Let me pull up what number are we looking at?
11 and 12.
11 and 12.
This is a friend's one. So it's
Let me do this. All right. So it says sketch the graph and then use that to determine the values of A for which the limit would exist, right? So I'm going to just draw the one for 11 because it's like the same process doing 12. You good with me just doing one or the other?
Could you do 12?
Sure. Yeah, that's fine.
With signs?
Yeah, no big deal. So I'm going to start by looking at x less than 0. So if I do that, the values for sine that I would be using, or the x values that I would be using to create my graph, would be like negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Well, 0, really, still. Okay. So if I plug 0 into 1 plus sine, sine of 0 is 0, and then I have the plus 1, right? Sine of negative pi over 2 is going to be negative 1, right? So plus 1 is going to be 0. Sine of negative pi is 0, and then plus 1. Sine of negative 3 pi over 2 is going to be positive 1, so plus 1 is 2. And then sine of negative 2 pi is back to 0 again, but I have the plus 1, so it's 1. So if I start drawing a picture of this, so like every tick mark is going to be half a pi. So I have open circle at 0, 1 because it's a strict or equal to inequality. And then I have 0, and then I have 1 again, and then I have 2, and then I have 1 again. So this thing is just going to kind of do that. Oops. Come back. Feel okay there?
Yeah.
Okay. Now I'm going to do the next part. So it's cosine between 0 and pi. And those are both are equal to's. So again, I'll do 0, I'll do positive pi over 2, and then I'll do pi. So cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1.
What is that called?
Unit circle.
Unit circle. Okay. I didn't even.
And here's the unfortunate part. The AP
Yeah.
is going to assume that you have that memorized.
Yeah.
We have to know like
I did last year.
I did.
everything in between that.
So here's what I would say. You for sure are going to need the quadrant list.
Yeah.
So the things that lie on the quadrants, 0, pi over 2, pi, 3 pi over 2, 2 pi, for sure you're going to want those. And they are, you will likely see, or I would say possibly see, things with pi over 3, pi over 4, pi over 6 are multiples of those.
Okay.
So like the entire unit circle. But here's the thing. If you know quadrant 1, you can extrapolate the whole thing from it just because it's the same thing with different signs, right? I'm going to keep going on this. Folks, do you have a question on this problem or is it something else?
I'm sorry.
Okay, I'm going to keep going then. Sam, you good?
Yeah.
I'm going to keep going. So here is pi over 2 and 0 there, and pi. So look what happens here. 0, 1. And that's going to be a filled in circle. So look, I end up filling in that open circle because this part that's defined at 0, 1. So I picked up that discontinuity there. And then
because is it less than or equal to?
Yeah.
Is it equal to? Okay.
Yep. And then I have pi over 2, 0. And I have pi negative 1. So I have that. And then my last piece is sine for pi greater than 0, or for x greater than pi. So again, we're starting at pi. We'll do 3 pi over 2. We'll do 2 pi. We'll do 5 pi over 2. And we'll do 3 pi. And that's a period. Everybody's okay there? So sine of pi is going to be
0.
0.
How do you know?
Sine of 3 pi over 2 is going to be negative 1. 2 pi, 5 pi over 2, positive 1. Because remember, that's pointing up, positive y coordinate. And then 3 pi again is at 0. So I have an open circle at pi 0. And then I have and just kind of does that for the rest of the. Okay, so we did the hard part, which was getting the graph. Okay, we still have to talk about the actual question. Because this question asked us to graph the thing and then do something with it, right? So we sketched the graph. Sam, you good with the sketch?
You got the sketch.
Okay. And it says, use it to determine the values for a in which the limit doesn't exist.
Oh, so it'll just be 2, right?
So, well, this is pi, right? Maybe we'll write it this way. And there's 2 others that I would write.
Well, as x approaches infinity.
Yes, and
Negative.
negative infinity. Very good. Why those ones?
This also.
Yes, perfect. Yeah. So I would list those ones also. So all other values of a, that limit exists and it's just equal to f of a. Right? So that was a lot of work. But really, where was most of the work? Getting the graph. If I had the graph to start with, this would have made, we spent 30 seconds maybe answering the question. That was the calculus question. The part before that was the pre-calculus part. On a test that I write for you, you think I'm going to have you spend potentially like 10 or 15 minutes trying to draw a graph of something that you should have been able to do from pre-calculus? No. No, I would not have you waste your test time doing that. I would just give you the picture and ask you the calculus question. My hope is that, yeah, there are some skills that, like, to do the calculus skill, you have to do the pre-calculus skill, but that's an unnecessary, let's tack on a lengthy pre-calculus skill to do a 30-second calculus skill, where it's like, now, the smart approach here that we're not ready for, but let me just say, we can revisit this question after we talk about continuity. But if I am looking at this with the knowledge that I now possess, having done this all and know what's coming, this is a continuous function, this is a continuous function, and this is a continuous function, right? That's okay? So the limit is going to exist for all continuous functions over their domain. So the only place that I need to worry about are these boundary values and possibly at infinities. So all I would check is when I plug 0 into this and to this, are they equal? And then plug pi into this and to this, are they equal? And then the limits at the end. Yeah. Oh my God. Stop. Is that? So again, picking, you don't know what continuity means yet, and why that would imply the limit exists. We'll get to that in the next section. So it's coming really quickly. That's why I felt like it was okay to mention it now. Sam. Happy. Okay, I think Brooks has been waiting for a minute. Do you have a follow-up on this one?
No.
Okay, we'll get to you after Brooks. And then you're...
I have a different one
Okay,
after.
yep. We'll just keep on going through the line. Sound good? Brooks, what's up?
Can I show you this question on my tablet? Is the limit, no, it does not exist? Or is it?
Well, it looks like it's going to 9.
Yeah, but like, it was like 9.001,
Well, it's getting, as we're getting closer to -4, it's getting closer to 9.
Okay, yeah.
So I would never plug in the value.
Yeah.
Like, it's gonna mess you up.
Thank you.
Yep. Who's next? Who was next? It was you?
Yeah.
Okay, Mary.
I have a question that's 2.3.
Yeah, let's do it. Tell me the number.
Number 31.
31 from there. Okay. $31, that guy right there. You said 31, right?
Yeah.
Yeah. Okay. Yeah.
I'm just so confused. And this tells me that. So the only switch for this limit is this one with
What am I doing here? I'm trying to write on this thing. I'll be right with you. Okay. Alright. So these 11 through 32 or whatever, I think these are excellent examples of the kinds of things that you would see on a homework quiz, as well as like the 2 infinity ones that we were looking at on the delta math. I think those make a good pair of sets of questions. So if I'm looking at this, the first thing I'm going to do is try a direct substitution. So if I do that, I get x cubed minus x cubed, so 0 over 0. That's indeterminate. So that doesn't work. So I'm going to have to algebra this thing. If I look at this, is there anything to factor? No. Is there a radical to rationalize, to like multiply by conjugate? No. The only thing I'm left with is to FOIL this thing, the quantity cubed out, right? Who remembers their Pascal's triangle that was going to make it easy to multiply this thing out?
Oh, it's like 5, 10, 10, 5, 10.
Well, row 3 is 1, 3, 3, 1.
Yeah.
So when I FOIL this out, it's going to just be x cubed plus 3x squared h plus 3x h squared plus h cubed. Now, if you didn't remember that, that's going to be tedious as all get out, right? Do you think that I, on a test or a quiz situation, would give you something where if you didn't remember Pascal's triangle, it's going to be really tedious to multiply it out? I would just have it squared. It's the same problem if it was squared, and then it's easy to multiply out. You would do it the exact same way. The cube just makes it longer unnecessarily, in my opinion. It's the same question, and just adding some tedium to it. Meredith, are you okay though?
Yeah.
Is that what you wanted to do, is multiply it out, and you're just like, this stinks, how do I do that?
Yeah, like I didn't get that, so I was just like confused.
Okay, but you're good so far?
Yeah.
Okay, so combine my like terms. X cubed cancels with x cubed. I notice now that everything on top has a h. So we'll just do a little reducey here.
Do you pull it out, or do you just take it completely? Just
I mean, you
there's
can.
one on the bottom.
I mean, you can think about factoring out and then reducing it all, or I just like knock one out of each of them because it's less writing to do. But like whatever works for you in terms of how you need to like track your work. Like they mean the same thing. I totally respect that if you have to do more or less, that is okay. But notice there's no denominator now, right? I'm just left with that stuff. And if I direct substitute now, I can't get an indeterminate form because I have no denominator. I just have up to 3x squared. And I plug h in for 0 for h.
Oh, like you're
And I'm done, right? I did the reducing, so let's try direct substitution again. And now, everything is wonderful. Right? I have some in front of you still, but yep, I'm circling through. Fellas in the back, are you guys, we're doing okay?
Yeah, we're
Okay.
working together.
Okay, that's fine. I just wanted to make sure that like, I hear a lot of this. I didn't know if you have about what we're doing or if it's just like other stuff that you guys are working through yourself, and that's fine that you're doing that. No problem for me.
Teachers, they're doing great.
Okay, good job, guys. So Meredith, happy?
Yeah.
You feel good?
Just one question.
Yeah, go ahead.
Have you used Pascal's triangle before? I've seen the like 1, 3, 3, but then there's like the h and x.
Right. So it's like 1x cubed, 1h cubed.
Oh, sorry, I didn't realize that the last one was. Okay, I'm good.
Okay. I'll just back those out because they're confusing. Okay. Who's next in line? Is it Adriana? Or is it who's-
Adriana can go.
Okay.
Can you do number 10 or 2.3?
2.3, number 10. Do I have 10 up here? No, it's the one before I have. Figures, Adriana. I'm just joking. It's totally fine. All right. We get it? Probably it's on the... Oh, this is like, got a lot of words here.
That's one.
Okay. So it asks, what is wrong with the equation x squared plus x minus 6 over x minus 2 is equal to x plus 3? It's a great question. It's one of the reasons why I signed it. What's wrong with that? Why isn't that equal?
Is the top part factorable?
It sure is. It factors to x plus 3 times x minus 2.
What?
It's not like you can do it at x.
Yes, Meredith is dead on. She's saying that when x equals 2, this is undefined, and this is 5. If the two things are equal, they need to be equal for all values of x, right? So when we reduce this, and we have like x plus 3 times x minus 2, we should have it's equal to x plus 3 except at 2. So this is what's wrong, is you didn't include the not equal at 2. Does that make sense? So why is this correct? If I stick a limit in front of it, it's fine. Why is it fine to have the limit in front of it?
Well, that basically means it's the asymptote on the bottom where it says it's going to 2. It basically tells you that the 2 is the asymptote, so it doesn't touch.
Well, it's kind of. It's more, but there's no asymptote here. What it is this. Does it matter for a limit if the function is defined there or not? No, it matters right up to that point, but it doesn't matter what happens at 2. So even though 2 is undefined, does that affect the limit? No way. Adriana, is that?
Yeah, I was just,
Yeah, and again, like, I didn't really write anything in words, but like, you know what I'm saying.
Yeah.
After talking through it, like, the picture speak, like, says a lot.
yeah.
Frank?
So when there's an open circle, the limit still exists, but it's just not defined in the function.
Right. So if this is f of x, and this is like x equals 2, the limit as x approaches 2 of f of x exists. Oops. Where did you go? But f of 2 is undefined.
Okay.
Right? And those two things can happen. The limit can exist even though the function has no value there. Or you could have this, where the limit doesn't exist and the function has no value there. So it doesn't, just because one is happening doesn't guarantee the other one does.
Okay.
Right?
Yeah.
Feel good? Absolutely. Okay. Lucia,
yeah.
I think it's you, and then Brooks, you're next.
Yeah.
Okay. Hit me, Lucia.
For delta math, the last limit to infinity, it doesn't, whatever's to the exponent, there's an x in the exponent, and I'm confused.
Okay. So type 3.
Yeah.
Alright.
Oh, okay.
Is this?
That's not what mine looks like, but
That's okay.
it'll still be helpful.
Alright. So what I'm going to do,
Yeah.
I'm going to look. What's the fastest growing thing on top?
X to 76.
Great. What's the fastest growing thing on bottom?
X to 12?
Yes.
Okay.
Log is super slow.
Yeah.
Slower than polynomial.
Oh, okay. Good to know.
So like in the order of fast,
Mm-hmm.
it's like constant slowest.
Okay.
Logs,
Yeah.
like I would say power function, that means like x to some real number.
Uh-huh.
So like whether it's a polynomial or it's like a radical function like 1/2 or like a mixed like 5/2 or even a decimal like x to the pi,
Mm-hmm.
like those are all just power functions.
Yeah. Okay.
And they go in order by size of the exponent.
Yeah.
And then biggest or fastest growing is exponential. So those dwarf all polynomials. So all I see here is bigger on top than bottom. So we say, well, they want us to say does not exist, even though this would be going to, I have a negative over a negative, so that's going to be like a positive leading coefficient for an even
Yeah.
degree. That should be going to positive infinity, but
So, going off what you just said, if they're opposite signs, that means they're odd.
if the exponent, you have to look at the exponent when you reduce it.
Okay.
So if I had like 75th over 12,
Mm-hmm.
75 minus 12 is an odd number.
Okay.
So that means it's going to be
That's how you know.
an odd function, where if it's negative,
Yeah.
it would flip, and now it's pointing down instead of pointing up.
Okay.
I mean, if the coefficient is negative,
Mm-hmm.
right, it like flips it.
Got it. Okay.
Does that make sense?
Yeah.
Okay, let's look at the next one. Maybe we'll get
See if there's
what you're looking at. Is that what we want?
not really. It's
Not
the same
really,
thing.
right?
It's bigger on the bottom.
Okay, so we should say 0.
Yeah.
Okay, the log doesn't matter. Let's go see if we get one.
Yeah. No.
No, what is this?
It's bigger on bottom.
Look at you cranking through this. Here you go.
Yeah, something like that.
Okay. So on top,
Uh-huh.
have an exponential.
Yeah.
Biggest thing on bottom is a
X to the 8.
polynomial.
Yeah.
Which one's growing faster?
You just said the top.
Exponentials are the fastest of all the fasties.
Okay.
So this one, the top growing faster. So we would say goes to positive infinity, but the delta math wants you say does not exist.
Got it. Okay.
Does that feel good?
Mm-hmm. Thank you.
Brooksy, just as your tablet beeps that it's dying here, what do you got?
That's not mine.
Oh, that wasn't yours.
Sounds like sticky.
Oh, sticky keys. Could be sticky keys.
So I said those three that are correct, but then I also said -3, -2, and 7 or 6. Why aren't those correct?
It says, okay. So it says for all the ones with a limit, the general limit is equal to 1.
Yeah.
So here at -2, the general limit does not exist because the left hand is on the right. Same thing in positive 6.
Yeah.
And here at -3,
Yeah, I mean,
the general limit is equal to 0. This guy's not
I think the question on it does that. So the left hand side is going 0, the right hand side is going 0. But at -3 is 1. How can we say that the general limit is -3 when -3 is equal to 1, right? Yeah.
So the limit is saying what should come next, not what does come next, what should. If we keep following the pattern,
Okay.
0 should come next,
Yeah,
but it doesn't.
Okay.
So the limit is not about what does, it's what should.
Yeah, okay, so it
So
has
think about
to
that.
be
Is that
Okay. Yeah. And also maybe it's not true.
absolutely? All right. I want to pause and do something of my own here real quick, since I think I burnt through the last round of questions before I grab someone else's. So, the hardest thing in calculus is knowing what to do and when to do it, right? That's what I want to talk about right now. For these limits that we've talked about so far, what we're going to talk about is how do I know what to do? Sound good? This sounds very interesting, right? The hardest part is like...
Well, I always asked that last year.
Okay. So you have some problem, right? The first thing you should ask, is that A finite?
What is finite? Like, it stops eventually? Is
It means that A is a number rather than
Infinite.
positive or negative infinity, right? So if it is finite, we'll do one set of stuff, and if it's not finite, we'll do another, okay? So if it is finite, you should just start with the direct substitution. After the direct substitution, you want to ask yourself, is it indeterminate? So like 0 over 0, infinity over infinity, negative infinity minus negative infinity, infinity to the 0, 1 to the infinity. That's 1, 2, 3, 4, 5. There's more that I'm missing. What are the other ones? Whatever. I'll just do dot, dot, dot. Really, these are the two, or, well, I should say, these are the three you'll likely see. The other ones are like, the algebra to get around them is just like not feasible for where we're at right now. And there's a better tool than algebra that I promise that we'll get to. That's the fix-it Felix hammer, where every problem is that every single one indeterminate problem is the same nail, where you just do the same thing. Okay. So if the answer is no, then you're just done, right? If it comes out, and you stop. If it is indeterminate, you got to do some algebra. So for you guys, what have we seen? We've factor and reduce, right? Was something that we could have happened. Make a least common denominator and add fractions. Yep. So multiply by the conjugate. And then we had like the like expand and simplify, right? And after that, we go back and do another direct substitution and try to use this.
Okay.
Does this feel so far so good?
So what?
Do like a pseudo direct substitution, because it's an infinity or negative infinity, you can't really plug those into a function. But you'd be like, okay, if I take this thing, it's like the top going to infinity or negative infinity, the bottom going to infinity or negative infinity. Just enough to see, right? And you'll ask us the same thing, is it indeterminate? If it's no, then you're done. If it's yes, we're just going to use growth rates. And that should get us to the finish line, right? Does that help kind of organize the skills that we've talked about so far, the basic problem types we've talked about so far? Builds a structure for you. It's like a decision tree that helps us know what to do when. Now, there's still some choice and there's still some art to it. Like when you're algebraing it up, making sure you're picking the right technique, that your algebra you're doing is correct, but like at least knowing that, hey, that I have to do something here because I tried plugging in and got an indeterminate, right? So it really, I think, helps clean up what to do. And we can expand on this as we pick up new skills and new techniques and new situations, but this is like kind of the basic framework. How does that feel? Adriana?
What is LCD stand for?
Least common denominator. Yes. Meredith.
I have another.
Yeah, 2.3 question? Sure. Is it from one of the ones that we just had up there already? Like
Yeah.
11?
It's number 29.
Perfect. I'm going to scroll up and grab that.
Yeah.
Okay. I want to start with a direct substitution, right?
Is this on the first or second homework? Second?
This is 2-3.
Okay.
Yep.
So the bottom one's always there.
So if I do that, if I start with the direct substitution, Meredith, I'm going to end up with, oops, I don't know why that disappeared, 1 over 0, right? So that's infinity, minus 1 over 0, that's infinity. Infinity minus infinity is one of our indeterminates. So I know I can't continue from here. So if I'm looking at this, I'm going to make a common denominator, and then maybe I'll have to still multiply by a conjugate later. We'll see. But it's looking kind of crappy. So if I do that, I'm going to have the limit. Oof. Hang on to your bottles there, guys. Is it right?
Yeah.
I'll have that, right? So far, so good. No simplifying can happen here. I mean, other than like separating it as two fractions and reducing it, going back to where we started. I don't want to do that. So looks like I'll be multiplying by a conjugate. Should I try to get rid of the square root in the denominator or the square root in the numerator? I would think the numerator, because that's where the addition and subtraction lives. So I'm going to have 1 minus 1 plus t over t times square root 1 plus t times 1 plus square root 1 plus t. And I'm not interested at all about multiplying that denominator out because it's in factored form right now. If I'm going to be able to do any reducing, I need that denominator in factored form to do the reducing. So I like it right the way it is. If I go and I distribute the negative in the numerator, I can combine the 1 and the negative 1, and I'm just left with negative t over. And now I notice I can reduce, right? Now that I've done a reducing, I was able to simplify and reduce something. Let's check our direct substitution again. I know I'm not going to get an indeterminate form because my numerator has no variable in it. So I can't end up with 0 over 0 or infinity over infinity because the numerator is just 1. It has to be. So I know I'm going to get an answer. I know I'm done with my simplification. So if I plug my 0 in, I'm going to have 0 over 1 times 1 plus 1. I'm sorry, 1 over. This is black.
1 over square root 1 plus t squared. So just 1 over t.
Oh, yep, thank you.
Plus root 1.
Where'd you get square root 1 plus 0?
Plug 0 in for t.
Oh, yeah.
That one. Meredith. Is that?
Yeah, that's good.
It's okay? Thanks, round.
I said, with this question, can you like say in words like the steps, like direct substitution, and then you multiply by the?
Yeah. So, you know, we did a ds up here, and we got indeterminate, right? So this is me making the least common denominator, right? And this is me multiplying by the conjugate. And this was me simplifying on that step. And here I reduced. And then from here to here was a direct substitution. Is this what you're looking for?
Yeah,
It's
that
just me
makes
to like
sense. Yeah.
add in the vocab on the step so you can associate it with the
Yeah.
chart.
Yeah.
Yeah, okay.
Thank you.
Of course. Okay.
It's like kind of direct substitution.
Lucy, is this on reference to this question or something?
No, something else.
Okay. Brooks, is this reference to this question or something else?
Something else.
Okay. So everybody good with this question before we move on?
Yeah.
Okay. Go.
That was math.
Okay.
Horizontal asymptotes with analytical limits,
Yep.
they have, it's like an e to the negative x and stuff, and I don't know how to.
Okay. So what is, let me just write it down because it's not, this is something specific that you're seeing.
Yeah.
Okay. Come on. Go away. All right.
So it's in parentheses.
No, you gotta give me limit as,
Well, it's
oh,
x
yeah, okay.
equals
It's y equals,
4x squared plus 2x cubed. And then that's in parentheses, and then on the outside, it's e to the negative x times e to the negative x.
okay, so like this,
Yep, exactly.
okay?
And it's give the equation of all horizontal asymptotes.
So that means that, right?
Yep. Okay.
So all I'm gonna do now, horizontal asymptotes are gonna happen when x goes to positive or negative infinity, right?
Okay.
So here, you're gonna have, at positive infinity, cubic over exponential. That just goes to 0, right?
Okay.
Now the negative, if I put a negative in down here, I have a negative exponent, right?
Yeah.
So that's really kind of the same thing as going to positive infinity of this with a positive exponent, right?
Yeah.
If I plug, this is just going to be like infinity times infinity, right?
Yeah. So it's infinity.
So that has no horizontal asymptote, right? Nothing is happening on this end. So I have just y equals 0.
Is there a way to type infinity on your taxes?
That's not an asymptote. It's not a horizontal asymptote. That is not contributing horizontal asymptote because that limit is going to infinity.
Okay.
So you just write y equals 0. That's the only horizontal asymptote.
How do you find is that y equals 0 as x goes to infinity?
Because I looked at this thing.
Yeah.
So it was polynomial on top, exponential on bottom.
Yeah.
This is growing faster than the top.
Yeah.
That's why it goes to 0.
Okay.
Just using your bobo, booba, bibi, ba, ba, ba.
Yeah, bigger on bottom.
Bobo
0.
botany.
Yeah.
On
Bobo
the
botany.
On the
I
ground.
think we should teach it to you so you understand.
Probably. I just like saying, I just like being able to say like weird noises. Ooh, bibi, booba. It's more fun that way.
Can you do one more example
I think we still have 10 minutes, so I can probably do lots more examples.
of the analytical?
You want me to just like delta math
That's
it
fine.
and look at, so everybody can see it?
Why is that?
I don't care, like one or it doesn't matter to me.
That's like if you have infinity, like the limit of x goes to infinity, you could plug infinity in and just see if it becomes 0. You know, like it's like the x is going to like 4, you took 4.
So Frankie,
Yeah.
horizontal asymptote is just what happens when the limit goes to positive infinity or negative infinity or both. So that's all I have to check for horizontal asymptotes. If it's a finite value, if either of them go to a finite value, those finite values are my asymptotes. If it's infinite, where the limit doesn't exist, doesn't contribute to an asymptote at all.
Okay.
So if I look at this one, for example, I'm just looking at a polynomial, right? Does polynomial have any horizontal asymptotes? No. I don't even have to do the limit, do I? No. This just has none. And I'm done.
Can I give you an example of one? Because this one has e to the negative 1 over x. And that's that confusing.
Yeah, let's see.
I know, like, what the heck? What is that?
Like this?
Yeah. Mine is just negative, but yeah, it looks like that.
Okay. So, if I send, let me just do this. Be easier to write
Yeah.
than say.
Yeah.
I'm gonna do. So if I'm doing this,
What's the question?
who wants the horizontal asymptotes for this?
How do you find it if it's not like
So the horizontal asymptotes are when the limit goes to positive or negative infinity. So that's all I'm going to check, are these infinite limits.
but in delta math that's DNA, right? Because how can a limit just be in infinity, you know?
Well, it's whatever this value comes out to be.
Okay.
So if this limit is a finite value, then like y equals that value is a horizontal asymptote.
Okay.
If this limit doesn't exist, or if it's infinite, then it doesn't contribute a horizontal asymptote. Okay, so far so good. Okay, so the way I'm going to think about this, and now I'm going to use, I want everyone to listen at what I'm about to do. I'm going to use some janky, sloppy notation here to start, and then show you how to do it with the proper notation. It's going to be easier to understand what I'm doing with the janky, sloppy notation, and then I'll talk you through how to do it the right way. But I think in terms of how do I really want to think about it, it's the janky way. How you want to write on your piece of paper, I'll show you the way to actually write on your piece of paper. I'm going to write it wrong here. Not wrong, but like improper, and then clean it up afterwards, okay? All right. So if I just push through my limit laws, I'm going to think about this as like,
Is that the same thing? Because mine just has f of x right now.
y equals,
So that limit stands for y as well. It couldn't.
well, this is just a function, right?
Yeah.
So like y equals is the
Okay.
same as f of x,
Yeah.
right?
Okay.
So I'm just looking at what happens to f of x when it goes to positive infinity or whatever, okay? So I'm going to do that, like, and then I'm going to push the limit into the exponent.
That's the sixth rule, right?
Kind of. We haven't really, I mean, we hinted at that composition can push the limit in via composition. So what's the limit as x goes to infinity of 1 over x?
Bigger on the bottom.
It's 0, right?
Yeah, bigger on bottom
There's
0.
no like
Yeah.
fraction, no. Okay.
1 over x,
Okay.
right? So the limit of 1 is 1. The limit of a constant is the constant. Then I have 2, and then I have e to the 0.
Even if it was negative 1 over x, it would still be 0.
Yeah,
Yeah, that's what I thought.
yeah, absolutely. And actually, this, what we did is fine. There's nothing wrong with this. I thought I was going to end up putting infinities in plugged into places, but I'm not. So,
I'm a little bit confused on that.
okay.
Oh,
I mean-
e to the 0 is 1.
Hmm?
So, how did I...
How did you find out 1 is to 0, or however you would say it?
So the limit as x goes to infinity of 1 over x
Yeah.
is 0, right?
Yeah.
So I had e to the limit
Mhm.
of 1 over x, so that's just e to the 0. Any non-zero number to the 0 is 1.
And what was the rule that you used to like separate the from the left hand side to right next to it? Like you.
So I
separate-
can distribute a limit across addition and subtraction.
Mhm.
I can then pull a constant out front, and then I can push my limit inside of a composition,
Yeah, I got you. For sure.
Okay.
okay?
Yeah, I kind of get it.
As long as everything is in the domain.
How does 1? I know I just asked this, but how does 1 to the power of whatever that? How did you find 0?
So I just did that limit is the 0.
Oh, as it goes to infinity, as x goes to infinity, it's going to be 0. Y is going to be 0. Okay, cool. And then, okay, and then why is 1 in parentheses right there?
E to the 0 is 1. Anything to the any non-zero to the 0 is 1.
This one right here, I'm trying to see if it's like special or something.
Oh, it just because so I'm showing that this is the limit of 1 plus
Yeah.
2 times. So this limit is applying only to the 1. That's why I wrote it there.
Okay. Is it because you can take like the term in front of it?
Well, I didn't want it to be confused to think it was this
Yeah.
or this. No. This limit is just applying to this number right here.
And then the plus 2e to the power of all that is an add-on.
A second term, right.
Okay.
Not inside this limit. Right? It's the difference between like f of x plus 3 versus like f of x plus 3.
Okay.
Right?
And what rule did you use that added the limit to the 1 over x? Which was that? Okay.
That I can, if I have a composition of two functions, I can push the limit inside the composition.
Oh.
Which is what I did, because I had e to the x composed with 1 over x.
Okay.
So I pushed the limit inside of the e to the x.
Cool.
So putting it to the negative infinity.
Yeah, so this is going to be not much different, right?
You put the push limit inside to 1 over x. Yeah.
So again, this is just
Equal to 0.
you just get the same thing. So this graph is going to look like
Take a breath and put ourselves in God's presence.
something like that.
God our Savior, help us recognize the opportunities we are given each day to make a difference in the lives of those around us.
Oh.
Give us the insight and
It'll
the
always go to
confidence
0.
to seize these opportunities. May we feel the peace that comes with bringing justice to others. May we feel the comfort that comes with reaching out to others. By believing in ourselves and in our abilities, help us make a difference in the world as we show our ardent love of neighbor. Notre Dame, speak the wisdom and pray for us. Have a wonderful Labor Day weekend.
Guys, I still have like 10 minutes or so. If you guys want to stay, if you have more questions, you're welcome to stay. But hit the road if you gotta go. Totally understand. How do you feel after today? Good. Like a lot better?
Yeah.
Does the flow chart help? Just as a way to visualize what it is we should be doing? Okay. So, ready for next time. It's gonna happen next time.
Thank you.
Unless you change your mind, which is nothing wrong.
Yeah, I know. Nothing wrong.
I have a question. When you have on Sunday, is it okay if I leave it like
Yeah. Yeah, for sure. For sure. No problem.
Thank you. Have a good one. Oh my God. You crazy.
I'm stopping the recording here, guys.
Yeah, no, that's